Okay, so you're going to take your notes over 10-6. Just follow along and fill in the blanks for me. Today we're going to change our focus a little bit from talking about the stoichiometry to talking about the energy involved in these reactions. So we know that there are two types of reactions, endothermic and exothermic. And we're going to use that knowledge to kind of figure out what these reactions tell us about an amount of energy released or consumed by the reaction. So let's just do a little review. The letter Q is used to represent heat. It consists of a value, the number, and a sign, positive or negative. If it's positive, energy is consumed by the reaction. And I'm just going to shorthand this, RXN, for reaction. If energy is consumed, it is endothermic. We'll get to that in a minute. If Q is negative, energy is released by the reaction. We'll talk about that a little more in detail, and that's called exothermic. We used this previously when we looked at the equation Q equals mc delta T, where Q is the amount of energy in joules, M stands for the mass, C stands for the specific heat of the metal or the substance, and delta T is the change in temperature. How much does that temperature change its temperature over a certain amount of time? So let me erase all this, and we're going to slide down. Wish I could make that bigger. Oh, I can. Okay. So we're going to erase all this. We're going to slide down. And let's talk about enthalpy. Enthalpy is the amount of energy contained in a substance. Enthalpy is what we call a state function. You can Google this later and look up all this stuff. We can't directly measure this. However, we can measure the change in enthalpy. So let's figure out what to put here. Enthalpies cannot be measured directly. However, change in enthalpy can be. And just like we did before, change for us is noted by a triangle, which means delta or difference. Change in H is the letter for enthalpy, is the enthalpy of the products minus the enthalpy of the reactants. This is known as the heat of, change that or to of, the reaction. And for us, delta H is equal to that Q. So before it was just heating a substance, but now it's actually going to be the heat given off by a reaction, by lighting something on fire, by mixing two substances together. How much energy is consumed or released? So we're going to slide down to chemical reactions. Be sure that you push pause if I'm going too quickly. Rewind this video. And we're going to go, we're going to go look at how this applies. Those two types of reactions we talked about, exothermic reactions, and don't worry about this little symbol thing. It just means that it wouldn't pull in my arrow or whatever I've tried to put in. Reactions in which heat energy is released. They generally feel warm or hot, and the energy of the reactants is greater, or you can just put the arrow, than the energy of the products. So greater than the energy of the products. Basically, the reaction energy diagram, if time is this way and energy is here, my reactants start really high and then they drop off to the products, which are really low. This change in energy here drops. So that's why we say it's negative. It drops. And endothermic are reactions in which heat energy is absorbed or consumed. You can think of it either way. They generally feel cool or cold, and the reactants for the energy is less than the energy of the products. So this one would look like this. We have to put that energy, that delta H here, change in energy, change in enthalpy. We have to put some in for this to occur. So it takes it from the surroundings and it feels cool. All right, so let me erase again. We're going to slide down. Again, if I go too fast, just rewind this, back it up. Oops, wrong button. Slide down. A blank equation is a chemical equation for a reaction that includes state conditions in which an equation is given a molar interpretation. I should probably be writing this. Write the word thermochemical here. Given a molar interpretation, that means it's balanced. And the enthalpy of the reaction for these molar amounts is written directly after the equation. So if you look here, this is methane burning in air. And here's my arrow. You'll see that on your paper. It releases CO2 and H2O. That's a combustion reaction. And the change in enthalpy for this equation, it releases 890 kilojoules. 890 kilojoules. So how do we use this? Well, we use this just like we did before. I use the molar numbers for each substance. And now I'm going to use the heat to solve these problems. So for every 1 mole of CH4, I release 890 kilojoules. You can leave the negative in there. And remember, a kilojoule is equal to 1,000 joules. Another energy unit is the calorie, but we'll come back to that later. So here's what we're going to plug in. If I need to cancel kilojoules, it goes this way. If I need to find energy, I put kilojoules on top and I just plug it in. Once you have moles of the substance, you just plug it in with kilojoules. Okay, so I'm about to reach the end here of this video time. So I'm going to go really, really quick. I'm going to solve the first one with you, then I'm going to ask you to do the rest, and I'm just going to put the answers up. Okay. All right. So sample problem. How much heat will be released when 4.77 grams of ethanol reacts? And they want how much heat? That means they want kilojoules. So I'm going to start with my given. And I went ahead and made it harder here. I've already put it in grams. So you're going to have to change it to moles. So go ahead and figure out how many grams of ethanol is in 1 mole of ethanol. Once you figure that out, plug it in and we'll keep moving. Okay, so that amount I think comes up to 46.08. I might be wrong on my math there. I did it quickly. And then for every 1 mole of ethanol consumed, look back at your reaction. 1 mole equals negative 1,367 kilojoules. All right, so you'll work out the math here. And you'll get, oops, try that again. Hush. You'll get 141.5 kilojoules released, which if I use my significant figures, I'll round that to 142 kilojoules released. All right, you look at the ones below, and then I'll post the answers and check your answers. Okay, in this next one, you're going to answer if it's endothermic or exothermic, so look here. And then you're going to figure out how much energy from 2.75 moles, okay? Okay, here are the answers for A and B. Push pause if you need another second, because I'm going to go and answer the last 2 sections. Okay, here are the last little bit. Check your answers, and then we're all done for the day. Good job.